The illusion of now. Right now, as you hear these words, you believe you are living in the present moment. You feel the weight of your body against whatever surface holds you. You sense the air entering your lungs. You are aware of a thought forming in the back of your mind, something about what comes next, or maybe something about what you had for dinner. All of it feels immediate. All of it feels like now. But here is something that might rearrange the way you think about everything you have ever experienced. The present moment, the only sliver of time you have ever inhabited, the only instant in which you have ever been alive, may not actually exist, not in the way you think it does, not as a universal, shared knife edge dividing the past from the future. According to some of the deepest ideas in modern physics, now is not a feature of the universe at all. It is a feature of you, and that changes everything. Consider this. Right now, at this very second, light from the sun is streaming toward the Earth. It left the surface of the sun about 8 minutes and 20 seconds ago. So when you look up at the sky and see that blazing disk of light, you are not seeing the sun as it is now. You are seeing the sun as it was over 8 minutes in the past. The photons striking your retinas are ancient messengers, relics of a moment that has already gone. And it gets stranger. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to reach us. The light from the Andromeda Galaxy takes about 2.5 million years. When you gaze at that faint smudge of light on a clear night, you are looking at a galaxy as it existed when our ancestors were still chipping stones into tools on the plains of Africa. So where exactly is now? If every piece of information reaching you from the universe is already out of date by the time it arrives, what does the present moment even mean? Is it just the collection of signals that happen to be arriving at your location at this particular instant? A hodgepodge of events from wildly different times, all masquerading as a single coherent moment. That question alone is enough to make you pause. But the strangeness goes far deeper than the speed of light, far deeper than the delay between an event and our observation of it. The strangeness reaches all the way down into the fundamental laws of physics, into the geometry of spacetime itself, into the quantum structure of reality, and into the biology of your own brain. From every angle, the present moment begins to dissolve the closer you look at it. Tonight, we are going to take that journey together. We will trace humanity's evolving understanding of time, from the earliest philosophers who grappled with its mysteries, through Newton's clockwork universe, into the shattering revelations of Einstein, and onward into the bizarre landscape of quantum gravity, where time itself may simply cease to exist. We will explore what your brain is actually doing when it constructs the sensation of now, and why that construction may be one of the most elaborate illusions in all of nature. And we will confront the profound, unsettling, and perhaps even beautiful possibility that the present moment, the only time you will ever know, is not what it seems. Let us begin where all explorations of time must begin, with the simple, overwhelming, undeniable feeling that time is passing right now. You feel it, don't you? The sense that this moment is real in a way that last Tuesday is not. Last Tuesday happened, sure. You might remember fragments of it, a conversation, a meal, the way the light fell through a window. But last Tuesday does not feel present. It feels gone, dissolved, swallowed by whatever mechanism consumes moments and transforms them into memories. And tomorrow feels equally unreal but in a different way. It is a blank space, a collection of possibilities that have not yet crystallized into fact. Only right now feels solid. Only right now feels like it is actually happening. This feeling is so fundamental, so deeply woven into the fabric of human experience, that questioning it feels almost absurd. Of course, the present moment exists. Of course, right now is real. What could be more obvious? And yet, The history of science is littered with things that were once obvious and turned out to be profoundly wrong. It was once obvious that the Earth was the center of the universe. It was once obvious that heavier objects fall faster than lighter ones. It was once obvious that time flows at the same rate everywhere, for everyone, in all circumstances. Every one of those certainties was eventually overturned by someone who had the audacity to look more carefully. The feeling that now is special, that it stands apart from the past and the future, that it is the unique moment in which reality actually unfolds, is perhaps the most deeply held intuition in human experience. Philosophers have a name for the view that only the present is real. They call it presentism. Under this view, the past no longer exists, the future has not yet come into being, and only the razor-thin edge of the present moment has any genuine reality. Presentism aligns perfectly with common sense. It matches the way we talk, the way we feel, the way we plan our lives. We treat the past as fixed and the future as open. We make decisions in the present, hoping to influence what comes next. The whole architecture of human thought seems built on the assumption that now is the only moment that matters, because now is the only moment that is. But what if common sense is wrong? What if the universe does not care about your sense of now? What if the equations that govern reality make no distinction between past, present, and future? What if the moment you call right now is no more special, no more real, no more privileged than any other moment in the entire history of the cosmos? These are not idle philosophical provocations. These are questions that emerge directly from our best physical theories, theories that have been tested to extraordinary precision and confirmed again and again by experiment. And the answers those theories suggest are, to put it mildly, unsettling. The ancient world grappled with the nature of time in ways that still resonate today. The Greek philosopher Heraclitus, writing around 500 BCE, compared existence to a river. "No man ever steps in the same river twice," he declared, "for it is not the same river and he is not the same man." For Heraclitus, change was the only constant. The present moment was a fleeting intersection of endless becoming, a snapshot in the ongoing transformation of all things. But his near-contemporary Parmenides took the exact opposite view. Parmenides argued that change was an illusion. True reality, he insisted, was eternal and unchanging. What we perceive as the flow of time is a trick of the senses, a veil draped over a deeper, timeless truth. The universe simply is whole and complete, with no past dissolving behind us and no future materializing ahead. These two positions, Heraclitus's world of perpetual flux and Parmenides's world of eternal stillness, established a debate that would echo through more than 2,000 years of philosophy and physics. And what is remarkable, what is almost eerie, is that modern physics has not resolved this ancient argument. If anything, it has deepened it. Perhaps the most famous wrestling match with time in the ancient world came from Augustine of Hippo, the Christian theologian writing in the 4th century. In his Confessions, Augustine asked a question so simple that it still stops people in their tracks. "What then is time?" he wrote. "If no one asks me, I know. If I wish to explain it to him who asks, I do not know." Augustine's frustration captures something essential about the problem. Time is the most familiar thing in the world and simultaneously the most baffling. We swim in it the way fish swim in water, so completely immersed that we struggle to see it clearly. Augustine went further, arguing that the past exists only in memory, the future exists only in expectation, and the present exists only in direct experience. But even the present, he noted, seems to shrink to nothing when you try to pin it down. The present year contains the present month, which contains the present day, which contains the present hour, which contains the present second, which contains what? An instant so brief it has no duration at all. If the present moment has no duration, then in what sense does it exist? And if it does have some duration, however brief, then part of it belongs to the past and part to the future, and you are right back where you started, trying to find the truth now within an ever-shrinking interval. This is the paradox that has haunted thinkers for millennia, and it is precisely where science begins. For most of human history, time was treated as a given. It was the stage on which events played out, the backdrop against which everything happened. Farmers marked it by the seasons. Sailors marked it by the stars. Philosophers argued about its nature, but the practical world moved forward on the assumption that time was universal, absolute, and straightforward. A second in ancient Rome was the same as a second in ancient China. Noon in Athens was the same kind of noon as noon in Babylon. Time was a river, and everyone floated on it together. This intuitive picture of time found its most precise and powerful expression in the work of Isaac Newton. In 1687, Newton published the Principia Mathematica, one of the most influential scientific works ever written. In it, he laid out his laws of motion and his theory of universal gravitation. But before he could describe how objects move, he needed to establish the arena in which movement occurs. He needed to define space and time. And so Newton made a declaration that would shape scientific thinking for more than 2 centuries. Absolute, true, and mathematical time, he wrote, of itself, and from its own nature, flows equably without relation to anything external. In Newton's universe, time was a perfectly uniform, perfectly universal river. It flowed at the same rate everywhere, in all circumstances, regardless of what was happening within it. A clock on Earth ticked at exactly the same rate as a hypothetical clock on Jupiter, or a clock hurtling through interstellar space. Time was the great equalizer, the one thing in the universe that could never be influenced, distorted, or altered. This Newtonian picture of time is deeply satisfying. It matches our everyday experience almost perfectly. The clocks in your house all agree with each other. When you synchronize your watch with a friend's watch, the two remain in step. Time seems to flow at a steady, universal, and completely reliable pace. But Newton's contemporary, the German philosopher and mathematician Gottfried Wilhelm Leibniz, was not convinced. Leibniz rejected the idea of absolute time. He argued that time was not some independent entity flowing through the universe. Instead, time was relational. It was nothing more than the ordering of events. Without change, without things happening in sequence, time had no meaning. You could not point to time as a thing in itself, separate from the events that occurred within it. The debate between Newton and Leibniz was one of the great intellectual confrontations of the Enlightenment. Newton's view dominated, largely because his equations were so spectacularly useful. They predicted the motions of planets, the trajectories of cannonballs, the tides of the ocean. Leibniz's philosophical objections, while intellectually compelling, could not compete with Newton's practical success. And so, for over 200 years, physics operated on the assumption that time was exactly what Newton said it was: absolute, universal, and indifferent to the events occurring within it. Time was the stage, and matter was the actors. The stage never changed. Until 1905, when a 26-year-old patent clerk in Switzerland looked at the equations of electromagnetism and realized that Newton was wrong. Albert Einstein did not set out to destroy the present moment. He set out to understand light. By the late 1800s, physicists had developed an extraordinarily successful theory of electromagnetism, thanks largely to the work of the Scottish physicist James Clerk Maxwell. Maxwell's equations described how electric and magnetic fields behaved, and they made a startling prediction. Electromagnetic waves, including light, always traveled at exactly the same speed. Not approximately the same speed, exactly the same speed. About 299,792 kilometers per second. Always. This was a strange result. In ordinary life, speeds add together. If you are standing on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour, the ball moves at 150 kilometers per hour relative to the ground. Speeds combine. But Maxwell's equations seem to say that light did not obey this rule. Light always moved at the same speed, regardless of how fast you were moving when you emitted it or observed it. Einstein took this seriously, more seriously than anyone else had. And in his 1905 paper on the electrodynamics of moving bodies, he explored the consequences of two simple assumptions. First, that the laws of physics are the same for all observers moving at constant velocities. Second, that the speed of light in a vacuum is the same for all such observers, regardless of the motion of the source. From these two principles, which he called postulates, everything else followed. And what followed was the unraveling of Newton's absolute time. The key insight is this. If the speed of light is the same for everyone, then something else must give. And what gives is simultaneity. Two events that appear simultaneous to one observer will not necessarily appear simultaneous to another observer moving at a different velocity. This is not an optical illusion. This is not a matter of delayed signals or slow processing. This is a fundamental feature of reality. Simultaneity is relative. Einstein illustrated this with a thought experiment that has become one of the most famous in all of physics. Imagine a train moving at high speed past a platform. Lightning strikes both ends of the train at the same time, as judged by an observer standing on the platform midway between the two strikes. The light from both strikes reaches this observer at the same time, and since the observer is equidistant from both strikes, they conclude that the strikes were simultaneous. But now consider an observer sitting in the middle of the train. The train is moving, so by the time the light from the two strikes reaches this observer, they have moved closer to the front of the train. The light from the front strike reaches them first. Since the speed of light is the same in all directions, the observer on the train concludes that the front strike happened before the rear strike. The two strikes were not simultaneous for this observer. Neither observer is wrong. Neither is making an error. They are both correct within their own frame of reference. Simultaneity, the notion that two things happen at the same time, depends on how you are moving. There is no universal now that everyone shares. Let that sink in for a moment. There is no universal now. This is not a subtle philosophical distinction. It is a concrete, measurable, experimentally verified fact about the universe, and its implications are staggering. In 1908, Einstein's former mathematics teacher, Hermann Minkowski, gave a lecture in Cologne, Germany that would reshape how we understand space and time. Henceforth, Minkowski declared, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union was spacetime. In Minkowski's formulation, the universe is not a three-dimensional space through which time flows. It is a four-dimensional object, a block of spacetime in which all events, past, present, and future, simply exist. There is no moving now that slides through this block like a cursor on a screen. There are only events, located at specific coordinates in spacetime, and the relationships between them. Think of it this way. Imagine you have a map of a long road stretching from one city to another. Every point on that road exists simultaneously on the map. The map does not flow from one city to the other. It just is. All the locations exist at once. Now imagine that the road is time and the map is space-time. Every moment from the beginning of the universe to its end exists on that map. The Big Bang is at one edge. Whatever the ultimate fate of the cosmos turns out to be sits at the other edge. And everything in between, including you reading these words right now, is just a point on the map. This is the block universe. And within it, your sense of now is no more fundamental than your sense of here. Just as here depends on where you happen to be standing, now depends on where you happen to be located in space-time and how you are moving through it. You do not experience all of space-time at once for the same reason you do not see all of the Earth at once. Your perspective is limited, but that limitation does not make the rest of space-time any less real. Now, this idea, known in philosophy as eternalism, is one of the most mind-bending concepts in all of science. It says that your birth exists, your death exists, every moment of your life exists, not in the past tense, not in the future tense, but in the eternal present tense of the block universe. The moment you took your first breath is just as real as the moment you are experiencing right now. It is simply located at a different coordinate in space-time. Dr. Christy Miller, the Joint Director of the Center for Time at the University of Sydney, has explained this in strikingly clear terms. When you talk about the present, she notes, you are really just describing your current location in space-time. That location changes, which is why it feels like time is passing. But the block itself does not change. The past is not gone. The future is not unwritten. They are both out there, somewhere in the fabric of space-time, as real and as fixed as the ground beneath your feet. If this makes you uncomfortable, you are in excellent company. The block universe has been debated by physicists and philosophers for over a century, and it continues to provoke strong reactions. Some embrace it as the most natural interpretation of Einstein's work. Others reject it, arguing that it strips the universe of genuine change, genuine becoming, genuine novelty. But the mathematical framework of relativity points in a very clear direction. If you take the equations seriously, and physicists generally do, then the block universe is not just possible. It is difficult to avoid, and the experimental evidence is overwhelmingly on Einstein's side. In 1971, physicists Joseph Haefel and Richard Keating performed one of the most elegant and direct tests of time dilation ever conducted. They placed cesium atomic clocks aboard commercial airliners and flew them around the world, once eastward and once westward. When the clocks returned, they compared them to identical clocks that had stayed on the ground. The results confirmed Einstein's predictions with remarkable accuracy. The clock that had flown eastward in the direction of Earth's rotation and therefore at a higher speed relative to the center of the Earth had lost time. The clock that had flown westward had gained time. The differences were measured in nanoseconds, billionths of a second, but they were real. Time had passed at different rates for the different clocks, and the evidence has only gotten more precise since then. In 2010, physicists at the National Institute of Standards and Technology used aluminum-ion optical clocks to measure time dilation between two clocks separated by a height difference of just about a foot, roughly 33 centimeters. The higher clock ticked faster. The lower clock, sitting in slightly stronger gravity, ticked slower. This was not a theory. It was a measurement. Then, in 2022, a team at JILA, a joint operation of the National Institute of Standards and Technology and the University of Colorado Boulder, pushed the precision even further. They measured time dilation across a distance of just 1 millimeter, about the width of a pencil tip. Over 90 hours of data collection, their measurement achieved a precision 50 times better than any previous clock comparison. And once again, The results were exactly what Einstein's general theory of relativity predicted. Time runs at different rates at different heights in a gravitational field. Period. This is not an abstract curiosity confined to physics laboratories. You rely on this fact every time you use a GPS navigation system. The GPS satellites orbiting the Earth move at about 14,000 kilometers per hour and sit roughly 20,200 kilometers above the surface. Both their speed and their altitude affect the rate at which their onboard atomic clocks tick. Special relativity predicts that their motion should cause their clocks to fall behind ground-based clocks by about 7 microseconds per day. General relativity predicts that their higher altitude, where gravity is weaker, should cause their clocks to run ahead by about 45 microseconds per day. The net effect is a gain of about 38 microseconds per day. If this correction were not applied, GPS positions would drift by about 10 kilometers per day. Your phone would send you to the wrong city. So the universe is quite literally telling us, in the most practical, down-to-earth terms imaginable, that time is not absolute. Time is flexible. Time depends on gravity and motion. And if time depends on gravity and motion, then there can be no single, universal now that applies everywhere in the cosmos. Consider what this means for a concept as basic as right now. You might feel that right now is the same everywhere, that this moment extends in all directions across the universe like a vast, invisible plane of simultaneity. But it does not. At this instant, on a planet orbiting a star in the Andromeda Galaxy, time is passing at a rate that depends on that planet's gravity and motion. There is no meaningful way to say that a particular moment on that planet is simultaneous with this moment on Earth. The concept of simultaneous does not apply across those distances and those differing gravitational conditions. Now on that planet and now on Earth are not synchronized. They cannot be synchronized. The universe does not provide a universal clock. And this leads to one of the most profound and disorienting conclusions in all of physics. If there is no universal present moment, then the distinction between past, present, and future is not a feature of the universe. It is a feature of the observer. It is, as Einstein himself put it in a letter written to the family of his lifelong friend Michel Besso, shortly after Besso's death in 1955, a stubbornly persistent illusion. Einstein wrote those words just weeks before his own death. People like us who believe in physics, he told the grieving family, know that the distinction between past, present, and future is only a stubbornly persistent illusion. Whether Einstein found this comforting, whether the idea that Besso's life still existed somewhere in the block of spacetime brought him any peace, we cannot know. But the physics was clear to him. The flowing river of time, the special significance of now, the sense that the present moment is uniquely real, all of it was, in Einstein's view, an artifact of human perception, not a feature of the cosmos. And if Einstein is right, then the question is not whether the present moment exists. The question is why it feels like it does. Why, if the universe is a timeless block, do we experience time as flowing? Why does the present moment feel so overwhelmingly real? To answer that question, we need to leave the realm of physics for a moment and look at something even closer to home. We need to look at the second law of thermodynamics. We need to look at entropy. And we need to understand why the universe has a direction at all. But let us slow down and truly inhabit the implications of what Einstein discovered, because the relativity of simultaneity is not just a curiosity of high-speed physics. It is a philosophical earthquake. It reaches into the most basic assumptions we make about reality and rips them apart. Imagine two friends, Alice and Bob. Alice is sitting on a bench in a park on Earth. Bob is aboard a spacecraft traveling at a significant fraction of the speed of light. passing the Earth at that very moment. At the instant their paths cross, both Alice and Bob agree on what is happening at their shared location. They can wave to each other through the window. So far, so good. But now ask a different question. What is happening right now on a planet in the Andromeda Galaxy, roughly 2.5 million light-years away? For Alice, sitting on her park bench, right now on Andromeda corresponds to a particular set of events. Maybe the inhabitants of that distant world, if there are any, are going about their daily lives. Maybe a particular star in that galaxy is in the process of exhausting its fuel. For Bob, zooming past at a substantial fraction of light speed, right now on Andromeda corresponds to a completely different set of events. Depending on the direction and speed of Bob's travel, his now on Andromeda could be days, weeks, or even years ahead of or behind Alice's now on Andromeda. He might be looking at a slice of Andromeda where that same star has already gone supernova, while Alice is looking at a slice where it is still shining peacefully. This is not because Bob's clocks are broken or because his information is delayed. It is because the very concept of now at a distant location depends on your state of motion. There is no fact of the matter about what is happening on Andromeda right now, independent of an observer's frame of reference. The question, what is happening there now, simply does not have a unique answer. This is sometimes called the Andromeda paradox, and it was articulated most clearly by the mathematician and physicist Roger Penrose. Penrose pointed out that if two people walking past each other on the street are moving at slightly different velocities, their respective now slices through the Andromeda Galaxy can differ by days. One person's now might include a fleet of alien warships that has already set out for Earth, while the other person's now might place the decision to launch that fleet in the future, not yet made. If the future is open and undetermined, this seems paradoxical. How can the same event be in the determined past for one observer and the undetermined future for another? The most natural resolution, the resolution that most physicists accept, is to say that both the past event and the future event already exist. They are both real. They are both part of the block. The distinction between past and future is observer-dependent, not a feature of the universe itself. And this is what drives many physicists, reluctantly or enthusiastically, toward the block universe interpretation. But the block universe is not the only game in town, and it is worth understanding why some physicists resist it. The growing block theory, for instance, accepts that the past is real and exists, but denies that the future does. In this view, the block of spacetime is not a completed four-dimensional object. It is a three-dimensional space that is growing, adding new layers of reality as time progresses. The past is fixed. The present is the frontier. The future is genuinely non-existent, an open space of possibilities that has not yet been actualized. This view has an intuitive appeal. It captures the common-sense feeling that the past is fixed and the future is open, while also accommodating the relativistic insight that the past is real, not something that has ceased to exist. But it faces a serious challenge from the relativity of simultaneity. If there is no universal now, then where exactly is the edge of the growing block? Different observers would disagree about which events are on the frontier and which are in the established past. The growing block seems to require a preferred frame of reference, a universal standard of rest, and that is precisely what special relativity says does not exist. Presentism, the view that only the present moment is real, faces even more severe difficulties. If only the present exists, then what does it mean for two observers in relative motion to disagree about which events are present? One observer's present includes events that the other observer places in the past or the future. If only present events exist, and the two observers disagree about what is present, then they disagree about what exists. This seems deeply problematic for a theory that claims to describe objective reality. Some philosophers have attempted to reconcile presentism with special relativity, but these attempts are controversial and have not gained wide acceptance within the physics community. The standard view among working physicists, to the extent that they think about these questions at all, is that the block universe is the most natural interpretation of relativity, even if it is not the only logically possible one. And there is another piece of evidence that pushes us further toward the block universe, one that comes not from abstract theorizing, but from the most familiar technology in the modern world. Your smartphone's ability to tell you where you are depends on a network of satellites orbiting the Earth, each carrying an atomic clock of staggering precision. These satellites broadcast signals that include the time at which the signal was sent. Your phone receives signals from multiple satellites, calculates the time difference, and uses those differences to triangulate your position. But here is the thing. Those satellite clocks do not tick at the same rate as clocks on the ground. They tick faster because they are higher up in Earth's gravitational field and therefore experience less gravitational time dilation. They also tick slower because they are moving at orbital speeds and therefore experience velocity-based time dilation. The net effect is that the satellite clocks gain about 38 microseconds per day relative to ground clocks. That sounds tiny, but because the speed of light is so fast, a 38 microsecond error would translate into a positional error of about 10 kilometers per day. Within a week, your GPS would be placing you in a different city. So every GPS satellite carries a clock that is deliberately set to tick at a slightly different rate before launch, pre-corrected to account for the relativistic effects it will experience in orbit. Your phone, in other words, relies on the fact that time is not absolute. Every accurate navigation fix you have ever received is a tiny, everyday confirmation of Einstein's deepest insight about the nature of time. And if these laboratory measurements and satellite corrections feel too abstract, too removed from everyday life, consider the most human version of this story, what physicists call the twin paradox. Imagine two identical twins born on the same day in the same hospital at the same instant. They grow up together, celebrate every birthday together, and age at exactly the same rate. Then, on their 30th birthday, one twin boards a spacecraft and accelerates to 90% of the speed of light. She flies outward into the galaxy for what, by her watch, is 5 years. Then she turns around and flies home at the same speed, another 5 years by her onboard clock. When she steps off the spacecraft, she is 40 years old. She is 10 years old. She has the wrinkles, the memories, the biological wear of a decade. But her twin, the one who stayed home, is not 40. He is nearly 53. He is almost 23 years old. His hair has grayed. His face has weathered. His children, who were toddlers when his sister left, are now young adults. A decade of his sister's life corresponds to more than 2 decades of his. This is not a thought experiment. This is a quantitative prediction of special relativity, confirmed by every time dilation experiment ever conducted. If we had the technology to accelerate a spacecraft to 90% of light speed, this is exactly what would happen. The traveling twin would return younger than the stay-at-home twin. They would have experienced different amounts of time. Their present moments would have diverged. And here is the part that truly dismantles our intuitive sense of now. During the trip, the two twins cannot agree on what time it is. They cannot agree on what is happening right now on each other's planet or spacecraft. The concept of the same time, simply breaks down when the twins are in relative motion. Each twin has their own present moment, their own slice through the block of spacetime, and those slices are tilted at different angles. What one twin calls now in the other's world does not correspond to what the other twin calls now. When the traveling twin is at the turnaround point, billions of kilometers from Earth, her now on Earth might correspond to a moment years ahead of or behind her brother's current experience, depending on the details of her motion. There is no fact of the matter about what is happening right now on Earth from her perspective, because right now is not a universal concept. It is a local one, defined by her own world line through space-time. The twin paradox is not really a paradox at all, once you abandon the assumption that time is universal. It is simply what happens when you take Einstein's insights seriously. Different paths through space-time accumulate different amounts of time. The present moment is not a shared platform that all observers stand on together. It is a private, path-dependent, deeply personal construction. Your now is yours alone. And this is not the only experimental confirmation. Time dilation has been measured with muons, subatomic particles produced by cosmic rays striking the upper atmosphere. Muons have a very short half-life, about 2.2 microseconds. At their speed, they should decay long before reaching the Earth's surface. But because they are traveling at close to the speed of light, time dilation stretches their lifetime, as seen from our frame of reference, by a factor large enough that many of them reach ground-based detectors intact. This was one of the earliest experimental confirmations of special relativity, and it has been repeated and refined countless times since. The evidence is overwhelming. Time is not what Newton thought it was. Time is not universal. Time is not absolute. Time is flexible, relative, and dependent on the observer. And if time is relative, then now is relative. And if now is relative, then the present moment, the moment you are living in right now, is not a universal feature of the cosmos. It is a local, observer-dependent construction. Let us go even deeper. Let us ask a question that you might not have considered before. How long is the present moment? This seems like it should have a simple answer. The present is instantaneous, a dimensionless point between past and future, right? That is certainly how we often think of it. The past stretches backward, the future stretches forward, and between them, infinitely thin, lies the present, the fleeting instant of now. But this picture has problems, deep, fundamental problems that philosophers have recognized for millennia. If the present moment has no duration at all, then nothing can happen in it. A truly instantaneous present would be a moment of zero length, and zero length means zero change, zero motion, zero experience. You cannot hear a note of music in an instant of zero duration, because hearing a note requires the sound wave to complete at least a partial oscillation, which takes time. You cannot see a bird fly past in an instant of zero duration, because seeing motion requires comparing the bird's position at one time with its position at another time. If the present is truly instantaneous, then it contains no experience at all. It is empty, blank, a mathematical point with no content. And so we are faced with a dilemma. If the present moment has no duration, it is empty. If it has some duration, then part of it lies in the past and part in the future, and we have not really identified a true now at all. We have only identified a short interval that straddles the boundary between past and future, and within that interval the same question arises. Where is the true present? Zoom in further. Where is it now? The present keeps retreating like a horizon that you approach but never reach. This is the puzzle that Augustine identified in the 4th century, that William James named the specious present in the 19th century, and that neuroscientists are grappling with today. And the resolution, to the extent that there is one, lies in understanding that the question itself may be misconceived. There may not be a true present to find. The present may not be a feature of the external world at all. It may be, as all the evidence suggests, a feature of the brain. This has an unexpected implication. If the present moment is generated by the brain, then it can in principle be different for different brains. A housefly, for example, has a much faster visual processing speed than a human. What a human perceives as a smoothly moving object, a fly may perceive as a series of discrete, flickering snapshots. The fly's now is not the same as your now, not just in terms of what it contains, but in terms of how it is structured. Different animals may experience time at different rates, not because time itself runs at different speeds for them, but because their brains sample and process the world at different speeds. To a creature with a very fast nervous system, the world may seem to unfold in slow motion. To a creature with a very slow nervous system, events may seem to blur together into a rapid, incomprehensible torrent. The present moment is not a fixed window. It is an adaptive construction, tailored to the needs and capabilities of the organism that generates it. And this raises a further question, one that carries us to the outermost edge of speculation. If the present moment is a construction of biological information processing, then what happens when the information processing stops? What happens to now when the brain shuts down, when you fall into a dreamless sleep, or when you undergo general anesthesia, or when you die? Your brain ceases to construct a present moment. But the universe continues. Events continue to occur. Particles continue to interact. Stars continue to burn. The block, if it exists, does not change. In dreamless sleep, you experience a gap, a period of no time that you bridge unconsciously. When you wake up, you pick up the thread of your present moment as if no time had passed, though of course hours have. For that gap, there was no now for you. There was no experience of the present. Time, in the subjective sense, did not exist for you during that interval. And yet the universe carried on without your now just fine. This suggests, powerfully, that the universe does not need the present moment. The present moment needs the universe, or more precisely, it needs a particular kind of complex, thermodynamically active information processing system embedded within the universe. Without such a system, there is no now. There are only events occurring at various coordinates in spacetime, related to each other by the laws of physics, and utterly indifferent to the question of which one is happening now. The universe does not experience a present moment. You do, and that distinction may be the most important insight in all of the science of time. Let us now turn to another dimension of this question, one that we have not yet fully explored. We have talked about what physics says about the present moment. We have talked about what the brain does to construct the present moment. But we have not yet talked about what the ancient contemplative traditions discovered about the present moment through centuries of direct, first-person investigation. Because long before Einstein wrote his equations, long before James named the specious present, long before neuroscientists mapped the temporal processing hierarchies of the brain, human beings were exploring the nature of now through the most direct method available: sustained, disciplined attention to their own experience. In the Buddhist tradition, which originated in South Asia around the 5th century BCE, the analysis of temporal experience is remarkably detailed and surprisingly consonant with modern science. The Buddhist concept of impermanence, or anicca in the Pali language, holds that all phenomena are transient. Nothing lasts. Every experience arises, persists for a moment, and passes away. The present moment in this framework is not a stable platform on which you stand. It is a process, a continuous rising and ceasing, a river that you cannot step into twice because it is never the same river from one instant to the next. Advanced Buddhist meditation practices are specifically designed to sharpen the mind's ability to perceive this moment-to-moment arising and ceasing. In Vipassana meditation, for example, practitioners train themselves to observe their sensory experience with increasing precision, noting the arising of each sensation, its brief persistence, and its dissolution. At deep levels of practice, meditators report that the apparently continuous flow of experience breaks down into a rapid series of discrete events, a flickering succession of moments so brief that ordinary awareness cannot detect them. This is strikingly reminiscent of what neuroscience tells us about the brain's temporal processing. The brain does not experience a continuous stream of consciousness. It processes information in discrete temporal windows, functional moments of roughly 30 to 50 milliseconds at the finest level, integrated into larger windows of 2 to 3 seconds at the level of conscious experience. The apparently smooth flow of time that you experience is constructed from these discrete packets, much as a movie creates the illusion of continuous motion from a sequence of still frames. The convergence between ancient contemplative insight and modern neuroscience is not proof that either is correct, but it is a remarkable coincidence, one that suggests both traditions are pointing at the same underlying reality. The present moment is not a simple, transparent window onto the world. It is a construction, a process, a dynamic interplay of sensation, memory, and expectation, all happening within a brain that evolved not to perceive ultimate reality, but to survive and reproduce in a particular ecological niche. And this brings us back, full circle, to the question we began with. What if the present moment does not really exist the way we think it does? The answer, based on everything we have explored, is this. It depends on what you mean by exist. If you mean, does the universe contain a universal, objective, observer-independent present moment that divides all of spacetime into a fixed past and an open future? Then the answer, according to our best physics, is almost certainly no. Relativity destroys this picture. There is no universal now. If you mean, does the present moment exist as a subjective experience, as a vivid, immediate, compelling feature of conscious life? Then the answer is an unequivocal yes. You are experiencing it right now. It is real in the sense that all experiences are real. It matters in the way that all experiences matter. The fact that it is constructed by your brain, rather than received from the external universe, does not diminish its significance. And if you mean, is there something special about the present moment in some deeper sense that we do not yet understand? Something that a future theory of quantum gravity might reveal? Then the answer is an honest, humble, scientifically appropriate, we do not know. The equations of general relativity suggest a block universe. The Wheeler-DeWitt equation suggests a timeless universe. Loop quantum gravity and string theory both suggest that time may not be fundamental, but none of these theories is complete. None of them constitutes a fully satisfactory theory of quantum gravity. The biggest unsolved problem in all of theoretical physics is how to reconcile quantum mechanics with general relativity. And the nature of time sits at the very heart of that problem. It is possible that, when we finally crack the puzzle of quantum gravity, we will discover that time is truly an illusion, that the block universe was correct all along, and that the present moment is nothing more than a mirage generated by thermodynamic brains in a timeless cosmos. It is also possible that we will discover that time is real, that the present moment has a genuine physical status, and that the timeless picture was an artifact of incomplete theories. Or it is possible, and perhaps most likely, that we will discover something entirely unexpected, something that nobody has imagined yet, something that reframes the question in a way that makes all our current arguments look quaint and naive. The way Newtonian mechanics looks from the vantage point of general relativity. The history of physics teaches us one lesson above all others. The universe is stranger than we think, and our theories are always provisional, always incomplete, always waiting to be superseded by something deeper. And so the present moment remains what it has always been, the most familiar thing in the universe and the most mysterious. You are living in it right now. You will always be living in it because there is nowhere else to be. Whether it is a fundamental feature of reality or an elaborate construction of your biology, whether it is a moving spotlight illuminating a frozen block or the growing edge of an evolving universe, it is yours. It is the arena of your entire existence. And the fact that science cannot yet fully explain it should not diminish your experience of it. If anything, it should deepen your wonder, because here you are, aware, alive, embedded in a universe that may be fundamentally timeless, and yet experiencing time with every fiber of your being. That is not just a scientific puzzle, it is the human condition, laid bare in its full, bewildering, astonishing glory. Here is something peculiar. Almost every fundamental law of physics works equally well whether time runs forward or backward. Take Newton's laws of motion. If you film a ball arcing through the air, a perfect parabolic trajectory, and then play the film in reverse, the reversed motion also obeys Newton's laws perfectly. The ball traces the same parabola, just in the opposite direction. Newton's equations do not care which way time is running. The same is true of Einstein's equations. The same is true of Maxwell's equations of electromagnetism. The same is true of Schrödinger's equation in quantum mechanics. Play the fundamental equations forward, play them backward, and the physics does not change. The laws themselves are time-symmetric. They treat the past and the future as interchangeable. And yet, your daily experience screams otherwise. You crack an egg into a pan, and the egg does not spontaneously reassemble itself. You pour cream into your coffee, and the cream does not unpour itself back into the little cup. You watch a glass fall off a table and shatter on the floor, and the shards do not leap up, fuse together, and return to the tabletop. Every moment of every day, you witness events that have a clear direction, an obvious before and after. The universe around you does not run backward. It has an arrow, and that arrow points relentlessly, unfailingly forward. The man who first articulated this idea in scientific terms was the British astronomer and physicist Sir Arthur Eddington. In 1927, during a series of lectures that would later be published as The Nature of the Physical World, Eddington coined the phrase, the arrow of time. He recognized that while the fundamental laws of physics were time-symmetric, the overall behavior of the universe was not. Something was imposing a direction on events, something that went beyond the individual equations governing particles and fields. That something is entropy. Entropy is one of those words that gets tossed around in popular science with varying degrees of accuracy. So let us be precise about what it means. In thermodynamics, entropy is a measure of the number of microscopic arrangements that could give rise to a particular macroscopic state. A highly ordered system, like a neatly stacked deck of cards, has low entropy because there are very few arrangements that produce that specific order. A disordered system, like a shuffled deck, has high entropy because there are countless arrangements that all look roughly the same, just randomly mixed. The second law of thermodynamics says that in any isolated system, entropy tends to increase over time. Disorder grows, order dissolves, hot things cool down, cold things warm up. Everything trends slowly and inexorably toward equilibrium, toward the most probable, most disordered state available. This is why your egg does not unscramble. The The scrambled state has enormously higher entropy than the intact state. There are trillions upon trillions more ways for the molecules in an egg to be arranged in a scrambled configuration than in an intact shell and yolk configuration. While it is not technically impossible for a scrambled egg to spontaneously reassemble, the probability of this happening is so staggeringly, incomprehensibly small that it would take many lifetimes of the universe for it to occur by chance. You would wait far, far longer than the current age of the cosmos and still not see it. And this is where the arrow of time comes from. Not from the fundamental laws of physics, which are perfectly time-symmetric, but from the statistics of large numbers. When you have a vast collection of particles, the overwhelming likelihood is that they will move from less probable states to more probable states, from order to disorder, from low entropy to high entropy. This is not a rigid law that compels every individual particle. It is a statistical tendency so overwhelming that it might as well be a law. It is the reason the universe has a direction. The Austrian physicist Ludwig Boltzmann, working in the second half of the 19th century, was the person who most clearly connected the dots between the microscopic world of atoms and the macroscopic phenomenon of entropy. Boltzmann showed that entropy could be understood in terms of probability. A low entropy state is simply an improbable state. A high entropy state is a probable one, and systems, left to themselves, naturally drift from improbable configurations to probable ones, not because there is a force pushing them, but simply because there are so many more probable configurations available. Boltzmann's insight was revolutionary, but it also raised a troubling question. If the laws of physics are time-symmetric, if every microscopic process can run equally well in reverse, then why does entropy increase toward the future rather than toward the past? The statistical argument works in both temporal directions. If you find a system in a low entropy state right now, the overwhelming probability is not only that it will be in a higher entropy state in the future, but also that it was in a higher entropy state in the past. The most likely explanation for any low entropy state you encounter is that it is a random fluctuation, a brief dip in an otherwise high entropy sea. This leads to one of the strangest ideas in all of physics, what is sometimes called the Boltzmann brain problem. If the universe is fundamentally trending toward maximum entropy, toward thermal equilibrium, toward a featureless soup of particles at uniform temperature, then the most statistically likely way for an ordered structure to arise is not through the gradual evolution of a low-entropy Big Bang. It is through a random fluctuation. And the smallest possible fluctuation that could give rise to a conscious experience is not an entire universe, or an entire planet, or even an entire human being. It is a disembodied brain, floating briefly in the void, equipped with just enough structure to have a single moment of conscious experience, complete with false memories of a past that never happened, before dissolving back into chaos. This sounds absurd, and it is. But the logic is airtight if you accept Boltzmann's statistical framework without any additional constraints. The probability of a single brain fluctuating into existence is unimaginably small, but it is still vastly more probable than an entire low-entropy universe fluctuating into existence. If we are just random fluctuations in a high-entropy cosmos, then we should expect to be Boltzmann brains, not inhabitants of a structured, orderly, 14-billion-year-old universe. The fact that we are not Boltzmann brains, the fact that we live in a universe with a coherent history, with galaxies and stars and planets and fossils, and a cosmic microwave background that tells a consistent story stretching back to the first moments after the Big Bang, tells us something profound. It tells us that the universe started in an extraordinarily low entropy state. The Big Bang was not just hot and dense. It was improbably ordered. And it is the slow, relentless unwinding of that initial order that gives rise to everything we call the arrow of time. This idea is known as the past hypothesis, and it was most clearly articulated by the philosopher David Albert and subsequently explored by physicists including Sean Carroll. The past hypothesis simply states that the universe began in a state of very low entropy. It does not explain why this happened. It is, in a sense, a brute fact, an initial condition that must be assumed in order for the rest of physics to make sense. But without it, the arrow of time dissolves. Without it, there is no reason for entropy to increase rather than decrease. Without it, the distinction between past and future evaporates. And so the arrow of time, the reason you remember yesterday but not tomorrow, the reason eggs scramble but do not unscramble, the reason you age and eventually die, all of it ultimately traces back to the extraordinarily special conditions at the beginning of the universe. The arrow of time is not a law of physics. It is a consequence of initial conditions. It is the echo of the Big Bang, reverberating through every moment of your life, giving direction to a universe whose fundamental equations have none. Here is a way to picture it. Imagine a vast, flat landscape, featureless in every direction. Now imagine that at one edge of this landscape there is a single tall mountain. If you place a ball at the top of the mountain, it will roll downhill. It does not matter which direction it rolls. It will always move from high ground to low ground. This is what entropy does. The low entropy beginning of the universe is the mountain. The passage of time is the ball rolling downhill. The direction of the roll is the arrow of time. And the flat, featureless plane at the bottom, stretching endlessly in all directions, is the heat death of the universe, the state of maximum entropy toward which everything is slowly, inexorably sliding. The heat death is not a dramatic cataclysm. It is the opposite. It is the ultimate anticlimax. It is a universe in which every temperature gradient has flattened, every energy source has been exhausted, every star has burned out, every black hole has evaporated through Hawking radiation, and every particle has drifted so far from every other particle that no interaction is possible. In this state, nothing happens. Nothing can happen. There are no processes, no events, no changes of any kind. And if nothing happens, then in what sense does time pass? If the arrow of time is defined by increasing entropy, and entropy has reached its maximum and can increase no further, then the arrow has nowhere to point. Time, in this terminal state, becomes meaningless. The heat death of the universe is not just the end of matter and energy. It may be the end of time itself. And so here is the deep irony at the heart of the entropic arrow. The very process that gives time its direction, the increase of entropy, also leads inevitably to a state in which time loses all meaning. The arrow of time is self-consuming. It points toward its own annihilation. The river of time flows toward a sea in which flow is impossible. But notice something subtle and important here. The second law of thermodynamics does not really explain why time flows. It explains why events have a preferred direction. There is a difference. The arrow of time tells you that entropy was lower in the past than it is now, and it will be higher in the future than it is now. But it does not tell you why you experience a moving, now, sliding along this arrow. It does not explain why you are aware of the present moment as something special and vivid, while the past is a fading memory, and the future is an uncertain anticipation. The arrow of time gives direction to the block, but it does not tell you why you feel like you are moving through it. To understand that, we need to turn to the organ that creates the feeling of now in the first place. We need to turn to the brain. Your sense of the present moment, the feeling that you are living in a continuous, flowing, unbroken stream of experience, is one of the most remarkable feats of biological engineering in the known universe. And it is, in a very real sense, a fabrication. When you look at the world around you, what you see feels immediate. A bird flies past your window and you see it in real time. A car honks its horn and you hear it in the present. Your friend says something funny and you laugh in the moment. Everything seems to happen now as it occurs with no delay. But this is not what is actually happening inside your skull. Every piece of sensory information reaching your brain has a processing delay. Light enters your eyes, strikes the retina, triggers a cascade of electrochemical signals that must travel along the optic nerve, pass through the lateral geniculate nucleus of the thalamus, and arrive at the visual cortex at the back of your head. Sound enters your ears, vibrates the tympanic membrane, is transduced by the hair cells of the cochlea, and travels along the auditory nerve to the auditory cortex in the temporal lobe. Touch, smell, taste, all of them involve physical signals that must be converted into neural impulses and routed through complex networks of neurons before they become conscious experiences. This entire process takes time. Not a lot of time by everyday standards, but a measurable amount. Visual processing, from photons striking retina to conscious awareness, takes somewhere between 50 and 150 milliseconds, depending on the complexity of the stimulus. Auditory processing is a bit faster, around 20 to 100 milliseconds. Tactile processing falls somewhere in between. The upshot is that by the time you become consciously aware of any event in the outside world, that event has already passed. You are always, without exception, living in the very recent past. But it gets more interesting than that. In 2020, a study published in the Proceedings of the National Academy of Sciences demonstrated something remarkable about how the brain handles moving objects. Researchers showed participants a moving object and recorded their brain activity using EEG. They found that the brain does not simply wait for visual information to arrive and then render it. Instead, the brain predicts where the object is going and pre-renders its expected position. In other words, the brain fills in the future before the sensory data arrives. When a moving object suddenly disappeared, the brain briefly continued to see it, projecting it forward along its expected trajectory until the new sensory information caught up and corrected the prediction. Your brain is not a passive recorder of the present. It is an active predictor that constructs the present by blending sensory data from the recent past with expectations about the near future. What you experience as now is not a faithful snapshot of an instantaneous moment. It is a best guess, a running estimate, a neural model that integrates information from slightly different times into a seamless, convincing, but ultimately constructed experience. The psychologist and philosopher William James recognized this over a century ago. In his landmark 1890 work, The Principles of Psychology, James introduced a concept he called the specious present. He argued that the present moment, as we experience it, is not an infinitesimal point. It is a short duration, what he described as a saddleback with a certain breadth, on which we sit perched, and from which we look in two directions into time. He wrote that the practically cognized present is not a knife edge, but a duration with a bow and a stern, a rearward-looking end and a forward-looking end. James estimated that this specious present lasted somewhere between a few seconds and about 12 seconds, though modern research has revised this downward. Current estimates suggest that the functional now, the duration over which the brain integrates information into a single coherent experience, is probably closer to 2 to 3 seconds, though this varies depending on the modality and the task. Some researchers have pointed to even shorter intervals for specific types of temporal discrimination. But the key insight is this: The present moment, as you experience it, has a duration. It is not a point. It is not an instant. It is a window, and that window is constructed by your brain, not dictated by the external world. Outside your skull, there is no such window. Outside your skull, events occur in a continuous, seamless flow that the laws of physics treat with perfect equanimity. It is your brain, and only your brain, that carves this flow into a special segment and labels it now. This has been further illuminated by the work of neuroscientists studying what some have called the window of presence, a concept developed by the philosopher and cognitive scientist Thomas Metzinger. Metzinger argues that consciousness constructs a model of reality that is centered on the present moment, a model that includes sensory data, memories of the immediate past, and predictions about the near future, all fused together into a single experiential field. This field feels like the present, but it is really a composite, a neuronal collage assembled from fragments of different times. Consider what this means. Your brain takes information that arrived at slightly different times, from slightly different events, and stitches it together into a coherent experience that feels simultaneous. The light from the far side of the room took fractionally longer to reach you than the light from the near side. The sound of a voice reached you after the sight of the lips moving. The sensation of your feet on the floor preceded your awareness of a bird singing outside. Yet all of these feel like they happened at the same time, in the same now. That synchronization is an achievement of your nervous system, not a feature of physics. The neuroscientist Mark Whitman, who has studied the perception of time extensively, has identified multiple levels of temporal processing in the brain. At the shortest level, below about 30 milliseconds, individual sensory events are not perceived as having any order at all. They are fused into a temporal snapshot. Between about 30 milliseconds and a few hundred milliseconds, events begin to acquire temporal order, a before and an after. And at the level of 2 to 3 seconds, the brain constructs a fully integrated present moment, a functional now that encompasses a brief window of lived experience. Think about what this means in concrete terms. Clap your hands. In the fraction of a second after your palms meet, your brain receives a burst of tactile information from the nerve endings in your skin, an auditory signal from the sound of the clap, and a visual signal from the sight of your hands coming together. These signals do not arrive at the brain simultaneously. Light travels faster than sound, and both travel faster than nerve impulses. The visual information reaches your visual cortex first, followed by the auditory information, followed by the tactile signal, and yet you do not perceive three separate events staggered in time. You perceive a single, unified clap, a seamless experience in which the sight, the sound, and the sensation all occur at the same instant. This is the brain performing an astonishing act of temporal editing. It is taking inputs that arrive at different times and stitching them together into a single coherent moment. The neuroscientist David Eagleman has conducted extensive research on this phenomenon, showing that the brain routinely reorders, delays, and adjusts the timing of sensory events to create the illusion of simultaneity. In one famous set of experiments, Eagleman and his collaborators demonstrated that when a new, unexpected delay is introduced between a voluntary action and its sensory consequence, the brain will, over time, recalibrate. It learns the new delay. And then, when the delay is suddenly removed, people actually perceive the consequence as occurring before their action. They experience the effect before the cause. The present moment, far from being a transparent window onto reality, is a post-processed narrative assembled by the brain after the fact. Benjamin Libet's experiments in the 1980s added another layer of strangeness. Libet found that the brain's electrical activity associated with a voluntary decision, what he called the readiness potential, begins approximately half a second before the person becomes consciously aware of having made the decision. In other words, your brain starts preparing for an action before you are aware of deciding to act. The conscious sense that you are making a choice right now, in the present moment, appears to be a retrospective narrative the brain constructs after the neural machinery has already set things in motion. These experiments are controversial and their interpretation is still debated, but they converge on a common theme. The present moment as you experience it is not a live feed. It is a highlight reel. Your brain receives a chaotic flood of sensory data from the external world, processes it through multiple stages of filtering, prediction, and integration, and then presents you with a polished, coherent, seamless experience that feels instantaneous, feels immediate, feels like now. But it is always slightly delayed, always slightly processed, always a reconstruction rather than a direct apprehension. The philosopher Daniel Dennett has used the metaphor of a multiple drafts model of consciousness to describe this process. In Dennett's framework, there is no single moment at which sensory data becomes conscious experience. Instead, the brain generates multiple versions of events, editing and revising them in parallel. And what you experience as the present moment is simply the version that happens to be dominant at any given time. There is no inner theater, no Cartesian stage where the present moment is displayed for an inner observer. There is only the process itself, the ongoing neural computation that generates the feeling of now as a byproduct of its own operation. This hierarchical construction of time perception has profound implications for the question of whether the present moment really exists. If the now you experience is a brain-generated construct with a definite duration, then it is not a feature of the external world. It is a feature of your cognitive architecture. A different brain might construct a different now. A faster brain might experience a shorter present. A slower brain might experience a longer one. A fundamentally different kind of information processing system might not experience a present moment at all. And here is where neuroscience and physics converge in a way that is both beautiful and vertiginous. Physics tells us that there is no privileged present moment in the external universe. Neuroscience tells us that the sense of a present moment is generated internally by the machinery of the brain. Put these two findings together and you arrive at a startling conclusion. The present moment is not something the universe gives you. It is something your brain builds for you. The universe provides events. Your brain provides the now. The cognitive neuroscientist Ruben Laukonen at the VU University of Amsterdam has taken this idea in an even more radical direction. In his research on meditation and consciousness, Laukonen has argued that the experience of the present moment is actually constructed from layers of abstraction. The brain does not simply receive raw sensory data and pass it along. It processes that data through a hierarchy of predictive models, each one more abstract and more removed from the immediate sensory input than the last. What you experience as the present moment is actually the output of this entire hierarchy, a richly processed, heavily interpreted, and deeply constructed version of what is actually happening. Laukonen and his collaborators have proposed that deep meditation practices, such as those found in Zen Buddhism and Theravada Buddhism, represent a journey deeper into the present moment, progressively stripping away the layers of abstraction to approach something closer to raw, unprocessed experience. And what meditators report at the deepest levels of this practice is extraordinary. The sense of self dissolves. The sense of time dissolves. The distinction between observer and observed dissolves. What remains is a kind of bare, contentless awareness that some traditions describe as timeless. This is not mysticism masquerading as science. This is a serious proposal about how the brain constructs temporal experience, one that is grounded in neuroscience and supported by neuroimaging data. And it suggests that the feeling of now, far from being a fundamental feature of reality, is a mid-level product of brain processing, one that can be altered, reduced, and in extreme cases, temporarily eliminated. So where does this leave us? Physics says there is no universal present. The brain constructs a local one. Entropy gives the block universe a direction but does not explain the sensation of flow. Everything points in the same direction. The present moment, as we experience it, is not a fundamental feature of reality. It is an emergent phenomenon, arising from the interaction between a time-symmetric universe, a statistical arrow imposed by entropy, and a brain that assembles a convincing simulation of now from scraps of recent sensory data. But not everyone is willing to accept this conclusion. Some of the most brilliant minds in modern physics have looked at the same evidence and drawn very different conclusions, and their arguments deserve to be heard. In a quiet farmhouse in the English countryside, not far from the town of Banbury, a physicist has been working for decades on an idea so radical that most of his colleagues do not know what to make of it. His name is Julian Barbour, and his claim is straightforward, uncompromising, and deeply strange. Time does not exist, not in any form, not as a flowing river, not as a frozen block, not as a background dimension, not as anything at all. Time is an illusion, and physics, Barbour argues, would be better off without it. Barbour is not a crank. He earned his doctorate at the University of Cologne, working on the foundations of Einstein's general relativity. He has published papers in respected journals, collaborated with prominent physicists, and earned the admiration of figures like Smolin and John Wheeler. But he has spent most of his career outside the traditional academic system, supporting himself as a translator of Russian scientific articles, working from his farmhouse, free to pursue lines of research that more conventionally employed physicists might not dare to explore. And the line of research he pursued led him to a breathtaking conclusion. In his 1999 book, The End of Time, Barbour argued that the universe does not exist in time. Instead, the universe is a collection of what he calls nows, individual, self-contained configurations of all the particles and fields in the cosmos. Each now is a complete snapshot of the universe, containing within it all the information needed to describe that particular arrangement of matter and energy. These nows do not occur in sequence. They do not flow from one to the next. They simply exist, all of them, all at once, in what Barbour calls Platonia, an infinite, timeless landscape of possible configurations. As we live, Barbour has said, we seem to move through a succession of nows, and the question is, what are they? For Barbour, each now is an arrangement of everything in the universe. We have the strong impression that things have definite positions relative to each other. Every instant of our lives is a particular arrangement of atoms, neurons, photons, and fields. And that arrangement, that specific configuration, is all that exists. There is no invisible river carrying us from one now to the next. There is no time flowing in the background. There is only the landscape of nows, and we are embedded within them. But if there is no time, why does it feel like there is? Barbour's answer is elegant and unsettling. Each now contains within it what he calls time capsules, internal records that look exactly like memories and traces of a past. The neurons in your brain right now are configured in a pattern that includes what feels like a memory of 5 minutes ago, or yesterday, or your childhood. But according to Barbour, those memories do not record actual past events. They are simply features of the current configuration. The now you inhabit right now includes brain states that are consistent with a past, But that past did not actually happen in any temporal sense. It is just part of the current structure. This is a staggering proposal. It means that your memory of this morning's breakfast is not a record of an event that occurred earlier in time. It is a structural feature of the present configuration of the universe, no more and no less. The cat that jumps, as Barbour has put it, is not the same cat that lands. Each moment is a complete, independent configuration, and the appearance of continuity is a pattern within those configurations, not a connection between them. If this sounds difficult to accept, you are not alone. The physicist Sean Carroll, a prominent cosmologist at Johns Hopkins University, has expressed skepticism about timeless approaches in general. The problem is not that I disagree with the timelessness crowd, Carroll has written. It's that I don't see the point. I am not motivated to make the effort to carefully read what they are writing, because I am very unclear about what is to be gained by doing so. And yet Barbour's ideas are not merely philosophical. They connect to deep mathematical structures within general relativity. When physicists reformulate Einstein's theory using a technique called the ADM formalism, named after its creators Richard Arnold, Stanley Desure, and Charles Misner, the result is a description of the universe that does not contain an explicit time variable. The universe, in this formulation, is described by a series of three-dimensional spatial geometries, and the dynamics emerge from the relationships between these geometries, not from their evolution along a time axis. And this brings us to one of the most important and most confounding equations in all of theoretical physics, the Wheeler-DeWitt equation. In 1967, DeWitt published an equation that attempted to combine quantum mechanics with general relativity. The origin story of this equation is wonderfully human. One day in 1965, John Archibald Wheeler, the great American physicist who had coined the term black hole and would later coin the term wormhole, found himself with a 2-hour stopover between flights at the Raleigh-Durham Airport in North Carolina. He called DeWitt, who was working at the University of North Carolina in nearby Chapel Hill, and proposed to meet at the airport during the wait. DeWitt showed up with the Hamilton-Jacobi equation of general relativity, a classical equation that Asher Peirce had published not long before. DeWitt had an idea. He suggested doing to this equation what Erwin Schrödinger had done to classical mechanics decades earlier, replacing the classical variables with quantum operators and turning the classical equation into a wave equation. Wheeler was tremendously excited by the idea, and the Wheeler-DeWitt equation was born. The equation describes the quantum state of the entire universe. It is, in a sense, the most ambitious equation in all of physics, and it has one immediately striking and deeply troubling feature. Time does not appear in it. Unlike Schrödinger's equation, which describes how a quantum system evolves over time and explicitly includes the time variable t on one side of the equation, the Wheeler-DeWitt equation has no time variable at all. It is, mathematically, a static equation. It describes a universe that, at the most fundamental level, does not change. This is known as the problem of time in quantum gravity, and it has been one of the central puzzles of theoretical physics for more than 50 years. Let that settle in your mind. The equation that physicists believe comes closest to describing the quantum state of the entire universe does not contain time. There is no clock ticking in this equation. There is no before and no after. There is no evolution, no development, no change. There is just a state, a single, frozen, timeless state. If this equation is correct, and admittedly it is not yet part of a complete theory, then time does not exist at the most fundamental level of reality. The universe simply is. The passage of time, the flow from past to future, the existence of a present moment, All of these familiar features of experience are emergent. They arise from deeper, timeless structures, in the same way that temperature arises from the motion of molecules. Individual molecules do not have a temperature. Temperature is a macroscopic property, an average, a statistical summary that only makes sense when you are dealing with enormous numbers of particles. Time may be the same kind of thing. It is real in the same way that temperature is real. It is meaningful and measurable and important. But it is not fundamental. It is not part of the bedrock of reality. It is a surface feature, a large-scale approximation that breaks down when you look too closely. DeWitt himself was deeply troubled by the implications of his own equation. The Wheeler-DeWitt equation, he later wrote, can be viewed as the Schrödinger equation of the universe. But the universe does not evolve in time. Time has disappeared from the equation. This disappearance of time is not a bug. It is a feature, one that emerges naturally when you try to apply quantum mechanics to the geometry of spacetime itself, rather than to particles moving within spacetime. The reason is deeply rooted in the structure of general relativity. In general relativity, time is not something external to the system. Time is part of the system. It is part of the spacetime geometry that the equations describe. When you quantize that geometry, when you apply the rules of quantum mechanics to spacetime itself, you quantize everything, including time. And when time is quantized, when it becomes part of the quantum state rather than a parameter that stands outside it, the familiar notion of temporal evolution simply evaporates. The equation does not describe a universe changing over time. It describes all possible configurations of the universe at once, a vast, timeless superposition of every possible geometry. If this sounds similar to the block universe of Einstein, that is because it is taken to its logical extreme. The block universe of special and general relativity says that all moments in time exist with equal reality. The Wheeler-DeWitt equation says that at the quantum level, the distinction between those moments dissolves entirely. There are no moments. There is no sequence. There is only the whole, the entire quantum state of the universe, outside of time. How then does time emerge from timelessness? This is one of the great unsolved questions in physics. One approach, proposed by the physicists Don Page and William Wooters in 1983, suggests that time can emerge from correlations within a timeless quantum state. Imagine a universe with two parts, a clock and everything else. Even in a timeless quantum state, the two parts can be correlated. When the clock reads 3 o'clock, the rest of the universe is in a particular configuration. When the clock reads 4 o'clock, the rest is in a different configuration. No time has passed. The entire state is static, but an observer inside the system, correlating the clock reading with the state of the rest of the universe, would experience what feels like the passage of time. Time in this picture is not a flow. It is a correlation, a relationship between subsystems within a timeless whole. This is extraordinary. It suggests that the feeling of now, the sensation that time is passing, the experience of one moment giving way to the next, could all be generated entirely by internal correlations within a static, unchanging quantum state. The universe does not evolve. We merely perceive it as evolving because we are embedded within it, and our perceptions are shaped by the particular correlations that our brains, as physical subsystems, are party to. The implication, if you take the equation at face value, is extraordinary. The universe, at its most fundamental level, is timeless. There is no evolution. There is no before and after. There is only the quantum state, eternally fixed, containing within it all the information about every possible configuration of matter and energy. But wait, if the universe is fundamentally timeless, then where does time come from? Where does the arrow of entropy come from? Where does the experience of a flowing present come from? One fascinating proposal came from physicists Don Page and William Wouters in 1983. They suggested that time could emerge from quantum entanglement. Imagine a hypothetical quantum clock entangled with its environment. The overall state of the combined system, clock plus environment, is timeless, just as the Wheeler-DeWitt equation describes. But if you ask the question, what does the environment look like when the clock reads such and such? You get a definite answer. The act of conditioning on the state of the clock, of asking what is happening at a particular clock time, creates the appearance of time from within a fundamentally timeless state. Time in this picture is not a background through which the universe evolves. It is a relationship between parts of the universe. It is relational, emergent, and observer-dependent. This idea resonates powerfully with the philosophy of Carlo Rovelli, the Italian physicist and one of the founders of loop quantum gravity. Rovelli, whose beautiful and haunting book The Order of Time has introduced millions of readers to these ideas, argues that time as we know it is not a fundamental feature of the universe. It is an emergent property that arises from our particular perspective as macroscopic beings interacting with the world through thermodynamic and informational processes. Rovelli's approach is to strip time of its properties one by one, like an archaeologist carefully removing layers of sediment to reveal what lies beneath. First, he removes the idea that time flows at a uniform rate. Einstein showed that it does not. Then he removes the idea that there is a universal present moment. Relativity shows there is not. Then he removes the idea that time has a built-in direction. The fundamental laws of physics are time-symmetric. Then he removes the idea that time is continuous. Quantum gravity suggests that spacetime may be granular at the smallest scales, composed of discrete units rather than a smooth continuum. And here we arrive at the Planck scale, the absolute bottom of physical reality as we understand it. The Planck time is approximately 5.39 times 10 to the negative 44 seconds. That is a decimal point followed by 43 zeros and then a 5. It is unimaginably, incomprehensibly tiny. The Planck time is to 1 second what 1 second is to approximately 17 billion years, far longer than the current age of the universe. This is the timescale at which the known laws of physics are expected to break down, where the smooth fabric of spacetime predicted by general relativity gives way to what John Wheeler called quantum foam, a seething, churning landscape of spacetime fluctuations so violent that the very concept of before and after may lose all meaning. At the Planck scale, the familiar structure of spacetime dissolves. Space and time as we know them may not exist at these scales. They may be emergent properties that arise only at larger scales, much as the smoothness of water emerges from the chaotic motion of trillions of water molecules. Look at a glass of water from a distance, and it appears perfectly smooth and continuous. Look at it through a powerful enough microscope, and it dissolves into a wild dance of individual molecules bouncing off each other. Spacetime may be similar. From our macroscopic vantage point, it looks smooth and continuous. But at the Planck scale, it may be anything but. This is the frontier where the search for quantum gravity lies. And it is at this frontier that the nature of time becomes most uncertain. The leading candidates for a theory of quantum gravity, including string theory and loop quantum gravity, both suggest in different ways that time is not fundamental. In string theory, the fundamental objects are vibrating strings in a higher dimensional space, and what we perceive as time emerges from the dynamics of these strings. In loop quantum gravity, spacetime itself is quantized, built up from discrete, indivisible units called spin networks, and time arises from the transitions between different spin network states. In both cases, at the deepest level, there is no time. There are only relationships, structures, and configurations. Time is what emerges when you zoom out, when you average over the quantum foam, when you move from the fundamental to the phenomenological. Rovelli, after stripping time of all its familiar properties, then asks the crucial question: if time is not fundamental, why do we experience it? And his answer, which draws on thermodynamics, information theory, and neuroscience, is both scientifically rigorous and deeply poetic. We experience time, Rovelli argues, because we are macroscopic systems embedded in a universe with a thermodynamic arrow. We interact with the world through processes that increase entropy. Our brains encode memories, which are low-entropy records of high-entropy events. Our bodies consume energy and dissipate heat. Every interaction we have with the world is mediated by the second law of thermodynamics, and it is this interaction, this particular perspective on the universe, that creates the sensation of temporal flow. In Rovelli's words, we are time. We are this space, this clearing opened by the traces of memory inside the connections between our neurons. We are memories. We are nostalgic. We are longing for a future that will not come. Time, for Rovelli, is not out there in the world. It is here in us. We are the clocks. We are the present moment. But not all physicists are willing to go this far. Some look at the same evidence and reach very different conclusions. And the most prominent of these dissenting voices belongs to Smolin. Smolin is a theoretical physicist at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. He is one of the founders of loop quantum gravity, and he has spent decades thinking about the deepest problems in physics. In his 2013 book, Time Reborn, Smolin made an argument that directly contradicts the timeless view of Barbour and Rovelli. Time, Smolin insists, is real, not just as an emergent phenomenon, not just as a useful fiction. Real, fundamental, the most basic feature of the universe. Smolin's argument begins with a critique of what he calls the Newtonian paradigm, the assumption that the universe can be described by timeless laws acting on initial conditions. This paradigm works beautifully for parts of the universe, for planets and particles and pendulums. But Smolin argues that it fails catastrophically when applied to the universe as a whole. You cannot stand outside the universe and observe it as a system. You cannot specify initial conditions from some external vantage point. The universe is not a subsystem of something larger. It is everything there is. And if the universe is everything there is, then the idea of timeless laws governing its behavior from the outside is, Smolin argues, deeply problematic. Where do these laws come from? Why are they the laws they are? If you say the laws are eternal and uncaused, you are not doing physics. You are doing theology. Smolin's radical proposal is that the laws of physics themselves evolve over time. They are not eternal truths inscribed in the fabric of reality. They are historical facts, contingent on the state of the universe, subject to change. And if the laws evolve, then time must be real, because evolution requires time. This is a minority view in theoretical physics, and it has attracted substantial criticism. But Smolin raises points that are difficult to dismiss. The block universe, for all its mathematical elegance, has trouble accounting for the overwhelming human experience of temporal flow. It has trouble explaining why the universe has such remarkably fine-tuned initial conditions. And it has trouble explaining the apparent openness of the future, the sense that what happens next is not yet determined. Smolin proposes what he calls a thick present, drawing on an idea that traces back to the philosopher Alfred North Whitehead. In this view, the present moment is not a knife edge between past and future. It is not a dimensionless point. It is a real, physical, causally active region of the universe, the only region that exists. The past has been and is gone. The future is not yet and may be genuinely open. Only the present is real, and it is within the present that the laws of physics operate, where causation unfolds, where new things come into being. Whether Smolin is right or wrong, his work highlights something important. The question of whether the present moment exists is not settled. It is an active area of research, a living debate within physics and philosophy, with brilliant minds on both sides. The block universe, the timeless universe, the evolving universe, these are not settled doctrines. They are competing hypotheses, each with strengths and weaknesses, each pointing toward different possible truths about the nature of reality. And perhaps that is the most honest thing we can say about the present moment. We do not know if it is real. We do not know if it is an illusion. We know that our experience of it is constructed by our brains. We know that the fundamental equations of physics do not single it out as special. We know that time dilation is real, that simultaneity is relative, that the universe may be fundamentally timeless at the Planck scale. And we know that despite all of this, the feeling of now is the most immediate, most vivid, most undeniable aspect of our existence. So what does all of this mean for you? Sitting here, breathing, thinking, existing in what feels like the present moment. Let us step back from the equations and the experiments and the competing theories and simply sit with the question for a moment. Because the question of whether now is real is not just a puzzle for physicists. It is a question about the nature of your life. Every experience you have ever had, every joy, every loss, every moment of boredom or beauty or terror occurred or seemed to occur in the present moment. If the present moment is not what you think it is, then what are those experiences? What are you? One of the most immediate and unsettling implications of the block universe is the question of free will. If the past, present, and future all exist with equal reality, then the future is just as fixed as the past. You cannot change the future any more than you can change the past, because the future is already out there in the block, as real and as immutable as last Tuesday. You're feeling that you are making choices, deciding between options, steering the course of your life, would be, in this view, nothing more than the subjective experience of a brain state that is itself a fixed point in the spacetime block. This is a genuinely disturbing idea, and it has troubled philosophers and physicists alike. If everything is determined, if the future is already written in the geometry of spacetime, then what is the point of deliberation, of effort, of moral reasoning? Why bother trying to make good choices if the choices have already been made? There are several responses to this concern, and none of them is fully satisfying. One response, favored by some philosophers, is compatibilism, the view that free will and determinism are not actually in conflict. On this view, free will does not require that the future be genuinely open. It only requires that your choices are caused by your own desires, beliefs, and reasoning processes, rather than by external coercion. You are free, in the relevant sense, as long as your actions flow from your own character, even if your character is itself a fixed point in the block. Another response comes from quantum mechanics. The standard interpretation of quantum mechanics, the Copenhagen interpretation, holds that the outcomes of quantum measurements are genuinely random, not determined in advance. If this randomness is fundamental, then the future may not be fully determined after all, and the block universe may not be the rigid, crystalline structure that the classical picture suggests. Instead, the block might be more like a branching tree, with quantum randomness generating genuine novelty at every fork. And then there is Smolin's response, which is simply to reject the block universe altogether and insist that the present moment is real, the future is open, and genuine novelty is possible. In Smolin's view, the universe is not a frozen four-dimensional object. It is a process, an ongoing act of creation, and the present moment is the leading edge of that process, the frontier where new things come into being. Each of these responses has its partisans and its critics, and the debate shows no signs of reaching a resolution anytime soon. But what is remarkable is how seriously the question is taken by working physicists. This is not an armchair debate among philosophers with no skin in the game. This is a question about the fundamental structure of reality, and the answer has implications that ripple outward through every domain of human thought. Consider, for example, the question of mortality. If the block universe is real, then your death, whenever it occurs, is a fixed event in spacetime. But so is your birth, and so is every moment in between. You do not cease to exist when you die. You simply stop existing at points beyond a certain coordinate in the time dimension. But the region of spacetime between your birth and your death is just as real, just as there, as it has ever been. In a block universe, you are never truly gone. You are always there, embedded in the fabric of spacetime, a pattern that persists not because time stops, but because time is not the kind of thing that flows. This was, in essence, the consolation Einstein offered to Besso's family. Besso had not truly departed. He had simply moved beyond the reach of Einstein's personal now. But in the deeper reality of spacetime, Besso's life was intact, preserved in the block like a photograph in an album that never deteriorates. Whether this is comforting or terrifying probably depends on your temperament. For some, the idea that every moment of their life persists forever in the geometry of spacetime is a kind of secular immortality, a scientific version of the ancient hope that nothing truly dies. For others, the idea that the future is fixed and that genuine freedom is an illusion is a kind of cosmic prison, a fate worse than ordinary mortality. But there is another way to think about it, and it is a way that brings together physics, neuroscience, and philosophy into something that might, just might, be genuinely useful. Perhaps the lesson of all this science is not that the present moment does not exist. Perhaps the lesson is that the present moment is not what we thought it was. We thought it was a feature of the external universe, a cosmic metronome ticking away in the background, dividing time into before and after. But it is not. The present moment is a feature of consciousness. It is something created by minds, by brains, by information processing systems embedded in a universe governed by thermodynamic arrow and statistical mechanics. And that makes it, in a way, even more remarkable. Think about what your brain is doing right now. It is taking in a stream of sensory data from an external world that has no privileged present. It is processing that data through a hierarchy of neural networks, each one operating on a slightly different timescale. It is integrating information from the very recent past with predictions about the very near future. It is constructing a seamless, coherent, vivid experience of a moment that, in terms of the fundamental physics, does not have any special status. And the result of all this processing, this staggeringly complex computational achievement, is the most familiar thing in your life. It is the feeling that you are here, that you are alive, that this moment is real. The universe may not have a present moment, but you do. Your brain creates one for you, fresh in every waking instant. And the fact that this experience is constructed rather than received does not make it less real. It makes it more extraordinary. You are not merely witnessing the present. You are generating it. This perspective invites a different relationship with the present moment. Instead of taking now for granted, as something the universe hands to you for free, you can appreciate it as a creative achievement of your own biology, the seamless flow of experience, the vivid immediacy of perception, the sense of being embedded in a living, breathing world. All of this is your brain's gift to you. It is the way your particular configuration of matter experiences the particular region of spacetime it inhabits. And in this light, the various contemplative traditions that emphasize present moment awareness take on a new dimension. When a Zen master instructs a student to be here now, the instruction is not just spiritual advice. It is an invitation to attend more closely to the brain's construction of temporal experience, to notice the way the present moment is assembled from fragments of sensation, memory, and expectation. The deeper you attend to the present, the more clearly you can see the machinery behind the illusion. And that clarity, according to both neuroscience and the contemplative traditions, can be profoundly transformative. Ruben Laukkonen and his colleagues have proposed that the progression of meditation is essentially a journey deeper into the present moment. As a meditator's practice deepens, the layers of abstraction that the brain normally imposes on raw sensory data begin to thin. Thoughts about the past and future become less intrusive. The narrative self, the running story you tell yourself about who you are and what is happening, becomes quieter. And what remains at the deepest levels is something closer to the bare experience of existing, stripped of the temporal scaffolding that the brain normally provides. Meditators who reach these deep states often report experiences that align strikingly with what physics suggests about the nature of time. They describe a sense of timelessness, a dissolving of the boundary between past, present, and future, a feeling that the ordinary flow of time has ceased. Some describe a sense of everything happening at once, or of the self dissolving into a wider, boundary-less awareness. These reports are subjective, of course, and difficult to study rigorously, but they are consistent with the idea that the feeling of now is a construct, one that can be altered by changing the brain's processing, and that beneath the construct lies something more fundamental, something that does not have the temporal structure we normally take for granted. None of this resolves the debate between those who believe time is real and those who believe it is an illusion. But it does suggest that the question may be more nuanced than either camp allows. Perhaps time is real but not fundamental. Perhaps the present moment exists but not in the way we think. Perhaps now is neither a fixed feature of the cosmos nor a pure illusion, but something in between, an emergent property that arises from the interplay of entropy, information, consciousness, and the underlying structure of space-time. The physicist George Ellis, a collaborator of Stephen Hawking and a leading figure in cosmology, has proposed what he calls the evolving block universe. In this view, the block of space-time is not static and complete. It is growing. The past exists, solid and fixed. The present is the boundary of the block, the edge where new space-time is being generated, and the future does not yet exist. It is genuinely open, indeterminate, waiting to be created by the processes occurring at the boundary. This is a middle path between the frozen block of eternalism and the flowing river of presentism. It preserves the insights of relativity while also accommodating the powerful intuition that the future is not yet determined. It suggests that the present moment is special after all, not as a universally shared instant, but as the growing edge of reality, the frontier where the possible becomes actual. Whether this view will ultimately be vindicated by a future theory of quantum gravity remains to be seen. But it offers a vision of time that is both scientifically informed and humanly meaningful. It allows the present moment to matter, not because the universe singles it out as special, but because it is the place where the universe is still being written. And so we find ourselves back where we began, in the present moment, the only time you have ever known. The physics is complex. The philosophy is unresolved. The neuroscience is revealing, but the experience is simple. You are here. You are aware. The world is presenting itself to you in all its richness and strangeness, and your brain is doing its best to make sense of it, to construct a coherent now from the flood of information pouring in from a universe that, at its deepest level, may have no now at all. This is the paradox of human existence. We live in a universe that may be fundamentally timeless, and yet we are time-bound creatures, organisms shaped by entropy, coded by memory, propelled by expectation. We cannot escape time. It is woven into every thought we think, every breath we take, every beat of our hearts. And yet when we look closely, time dissolves. The present moment shimmers and recedes like a mirage on a desert highway, always just ahead, always just out of reach. But perhaps that shimmering is not a flaw. Perhaps it is a feature. Perhaps the beauty of the present moment lies precisely in its elusiveness, in the way it refuses to be pinned down, in the way it keeps emerging, moment after moment, fresh and unrepeatable and utterly mysterious. The physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." Something similar might be said about time. Nobody fully understands time, not the physicists who write the equations, not the philosophers who parse the logic, not the neuroscientists who map the brain, not the meditators who sit in silence, watching the present moment arise and pass away. But we keep asking the questions. We keep probing, keep measuring, keep wondering. And that perhaps is the most human thing of all. We are the part of the universe that wonders about itself. We are the part of the cosmos that asks, what is now? And even if the answer turns out to be that now is an illusion, that the present moment does not exist in the way we thought it did, the asking itself is real. The wonder is real. The curiosity, the awe, the relentless drive to understand, those are features of this moment, this particular configuration of matter and energy, this precise location in whatever spacetime turns out to be. And so here we are, in the present moment, the moment that physics says may not be privileged, the moment that neuroscience says is constructed, the moment that philosophy cannot quite define, the moment that, despite all of this, feels more real than anything else in the universe. Perhaps that is enough. Perhaps the deepest truth about the present moment is that it does not need to be metaphysically fundamental to be profoundly meaningful. It does not need to exist in some absolute sense to be the arena in which your entire life unfolds. The universe may not have a present, but you do, and you are living in it right now. Whatever right now turns out to be, because in the end, that may be the deepest truth of all. The universe hands us a mystery. Physics strips away our assumptions. Neuroscience reveals the machinery behind the curtain. Philosophy sharpens the questions until they cut. And after all of it, after the equations and the experiments and the centuries of wondering, we are left standing exactly where we started, in a moment that feels real, that feels immediate, that feels like the only thing there is. A moment that the universe itself may not recognize, that the equations do not single out, that the brain constructs from fragments and predictions and guesswork. A moment that is, by every measure we have, both the most intimate feature of our existence and the most elusive puzzle in all of science. And maybe that is not a contradiction. Maybe that is what makes it beautiful. You have been watching the entire history of the universe. If this journey through the mysteries of time blew your mind, or maybe even changed the way you see the present moment, please consider hitting the like button and subscribing to the channel. Leave us a comment and let us know what you think. Is the present moment real, or is it the most convincing illusion in the cosmos? We would love to hear your thoughts. Thanks for watching, and we will see you next time.